we spoke about the type of activity that takes place at the chemical synapse. And this is what's happening on the postsynaptic side here. So just to jump back a bit, we talked about the ionotropic receptors and really understanding that the channel for ion movement was also the receptor. So there was an area here where the neurotransmitter that's being released from the presynaptic side would come and bind onto this receptor. And because the receptor is also the channel, it opens right away and we have easy ion movement. Right? Let's compare that to the metabotropic receptor. The metabotropic receptor is different in that it's coupled to a protein. This is your protein here, your G protein. And the G protein is really responsible for carrying out a sequence of events inside the cell that can bring about that response. So the receptor does nothing else. It's not acting as a channel. It's not doing anything but relaying the signal to this protein, which it's coupled to bring about a sequence of events inside the cell. There are two options for those sequence of events. The first one is the second messenger system. The second messenger system, this protein, specifically the alpha subunit here, is going to dissociate off. It's going to travel downstream to an enzyme that's in the membrane, activate that enzyme. This enzyme can be several different things. We'll talk about some examples. But essentially, that enzyme is what we call an amplifier enzyme. It's going to really make a big or sequence of events inside the cell and amplify this response. It's going to make it bigger than just having one neurotransmitter bind onto this one receptor. And so it creates lots of second messenger, usually cyclic AMP, but it can be other things. So the enzyme generates lots of this cyclic AMP, and that cyclic AMP can go into the cell and do different things. It can open up channels, it can turn on proteins, and in that way, the binding of that neurotransmitter onto this metabotropic receptor slowly, right, it's going to be much slower, slowly brings about cellular response. It's not direct, right? It needs the help of these messengers. That's why we call them second messengers. They are bringing about the response that was initiated by the binding of this neurotransmitter. Okay, it's like having a bunch of middlemen. So like I tell you to do something, and then you amplify the response by telling 10 other people to go do it. Okay, so that's what we have with the second messenger system. So as opposed to me doing something 10 times, I can tell you and you can tell 10 other people, and that will amplify my response. It'll be slower though. It'll be much slower than if I just went and did it myself. Okay. The second option for the metabotropic receptor here is the direct coupling. So the direct coupling is also, the receptor is also coupled to a G protein, but the dissociation of the alpha subunit does something different. It doesn't turn on an enzyme the way it does in the second messenger pathway. Instead, it's going to bind onto an ion channel and open that channel. So it's like a midway point between the ionotropic receptor and the second messenger system. This protein is going to dissociate off and open up an ion channel somewhere else in that membrane. Alrighty, and so what we have is, again, that same response being brought about. It's just a delay happening here. And we don't have the production of the second messenger. We don't have an amplifier enzyme. All we have is the protein that receptor is coupled to, moving downstream in the membrane and turning on a channel, opening up a channel. Okay. So there will be a delay here as well, not quite the delay that we see with the second messenger system, simply because it's similar to the ionotropic receptor, but there is a bit of delay because we have the G protein coupled to this receptor. Okay, does that make sense in terms of differentiating between ionotropic and metabotropic, and then further differentiating between the second messenger system and then direct coupling system?
So then, the direct coupling system, when that alpha protein goes down and binds with the ion channel. So does that ion channel not have any receptor binding sites on it, or?
No, it's not a receptor. This ion channel is not a receptor. Okay, it's just a channel. And this is one of the channels that we spoke about, we've spoken about, the ligand-gated channels, sodium or potassium channels that are in the membrane. Okay, these can be your leak channels that we've also spoken about. But this channel is not an ionotropic receptor. It's not a receptor at all. Right, it's just a channel. The metabotropic receptor is where that ligand is binding, that neurotransmitter. Okay. And now, whether or not, depending on the type of channel that this is, if it's a sodium channel and we open up the sodium channel, we're going to depolarize the membrane. If it's a potassium channel and we open up the potassium channel, are we going to depolarize? No, we're going to kick potassium out. We're going to hyperpolarize the membrane. So depending on what this channel is, will determine if we have an IPSP or an EPSP. And then when we sum all of those IPSPs and EPSPs together, that will determine whether or not that second neuron fires another action potential if it gets the threshold. All right, so these are the pieces that are really fitting into a bigger puzzle of understanding the synapse, right? Determining what type of channel this is, what type of ion is moving, whether it's increasing the membrane potential or decreasing the membrane potential.